Hello sleepy science subscribers, welcome to the channel. Please do not forget to like and subscribe so more people can benefit from these calming journeys. Tonight we begin a calm and detailed exploration of one of the most profound questions in modern cosmology: how the universe will eventually reach its final stage. This topic involves the study of cosmic expansion, thermodynamic limits, gravitational evolution, and quantum processes, all of which contribute to long-term predictions about the fate of everything that exists. As we move gently through this subject, the aim is not to create fear, but to present the scientific understanding of how the cosmos evolves according to stable physical laws. The universe has been expanding since the Big Bang, an event that occurred approximately 13.5 billion years ago. Evidence for this expansion comes from the redshift of distant galaxies, which indicates that space itself stretches over time. This expansion is not like objects moving through a pre-existing space. Rather, it is the metric of space increasing in scale. As galaxies drift apart, large-scale structures become more separated, and the average density of the universe decreases gradually. This process sets the stage for long-term cosmic behavior, because the rate of expansion influences every prediction about the universe's final state. One major factor in understanding the future of the universe is dark energy. This mysterious component makes up most of the universe's total energy content, and it exerts a repulsive effect that accelerates expansion. Observations of supernovae in the cosmic microwave background show that this acceleration is increasing. If dark energy remains constant or continues to grow, the universe will expand forever, with regions becoming increasingly isolated. In such a scenario, galaxies outside our local group will eventually move beyond the observable horizon. Over countless trillions of years, the night sky would grow darker as distant galaxies fade from view due to the relentless expansion of space. Another layer of the universe's long-term evolution involves the life cycle of stars. Stars burn hydrogen and other elements through nuclear fusion, producing light and heat while generating heavier elements. However, stars cannot burn forever. Over extremely long timescales, stars exhaust their fuel and transform into dim remnants such as white dwarfs, neutron stars, and black holes. Current models predict that star formation will gradually decline as available gas becomes scarce. Eventually, the universe will enter an era in which new stars no longer form, leaving only the remnants of older generations. This stellar evolution contributes to the gradual dimming of the cosmos and moves the universe toward a colder and darker state. Thermodynamics provides another important perspective on the universe's future. The second law of thermodynamics states that entropy, a measure of disorder, tends to increase in closed systems. The universe behaves like such a system on large scales. As stars burn out and energy spreads thinly across expanding space, the universe approaches a condition known as heat death. In this state, temperature differences become minimal, preventing any meaningful energy transfer. Without energy gradients, physical processes slow dramatically. Motion, heat flow, and structure formation reach near zero activity. The universe would then exist in a state of maximal entropy, cold, dark, and nearly inert. Gravitational processes add more complexity to predictions about the universe's fate. Over time, black holes will dominate large-scale cosmic structure. As stars collapse or merge, many will form black holes that slowly accumulate matter. Yet even black holes are not eternal. According to Stephen Hawking's theory of black hole evaporation, they emit radiation known as Hawking radiation. This radiation causes black holes to lose mass over extremely long periods. The largest black holes may take unimaginable lengths of time to evaporate, but eventually they too would disappear. The final stage of this process leads to a universe with no black holes, no stars, and no significant sources of energy. Quantum mechanics contributes additional possibilities. In some models, dark energy may not remain constant. If dark energy increases rapidly, the universe could face a scenario known as the Big Rip. In this prediction, the expansion accelerates to the point where galaxies, stars, planets, and even atoms are torn apart by the growth of space. This outcome depends on the exact properties of dark energy, which remain uncertain. While current observations favor a more stable form of dark energy, the possibility of a dynamic and destructive future cannot be entirely dismissed. There are also theoretical models involving cyclical cosmology, in which the universe undergoes repeated cycles of expansion and contraction. These models propose that after expanding, the universe could reverse into a big crunch, collapsing under gravitational pull before potentially rebounding into another expansion. However, current measurements of dark energy make this scenario less likely, because the observed acceleration indicates that contraction is not occurring and appears unlikely to occur in the future. Some researchers consider the possibility of vacuum decay, a quantum process in which the universe could transition from its current energy state to a lower one. This transition could propagate at high speed, altering the laws of physics in its path. Although the probability of such an event appears extremely low, it remains part of theoretical discussions about cosmic endings due to the nature of quantum fields. Each of these possibilities highlights different aspects of physical law. Whether the universe ends through heat death, black hole evaporation, vacuum decay, or accelerated expansion, all predictions rely on consistent observations of cosmic behavior. Despite the immense timescales involved, these scenarios remain within the framework of known physics. The universe's future therefore remains a profound and ongoing subject of scientific inquiry, shaped by thermodynamics, relativity, quantum mechanics, and observations of cosmic expansion. Understanding the long-term fate of the universe requires examining the physical processes that govern matter, energy, and space-time on both microscopic and cosmic scales. After the earliest stages of expansion, the universe entered a period in which matter dominated over radiation. Galaxies formed through gravitational collapse, stars ignited through nuclear fusion, and large-scale cosmic structures emerged from small fluctuations in density. As time passes, the influence of matter decreases relative to dark energy. This shift marks a transition from a universe shaped primarily by gravitational attraction to one shaped by the accelerated expansion driven by dark energy. This transition sets the foundation for predictions about the extremely distant future. In the near future, on cosmic scales, meaning tens of billions of years, stars will continue their life cycles. Massive stars will collapse into black holes or neutron stars, while less massive stars, like the Sun, will become white dwarfs. Eventually, the interstellar gas necessary for star formation will be depleted. Galaxies will grow dimmer as older stars fade, and no new stars replace them. This period is often referred to as the degenerate era, because the objects remaining will be primarily stellar remnants, such as white dwarfs, neutron stars, and black holes. During this era, the universe will take on a different character as luminous activity declines. As trillions of years pass, white dwarfs will cool and transition into black dwarfs, cold remnants composed of carbon and oxygen that emit almost no radiation. These objects represent the final stage of stellar evolution for sun-like stars. Neutron stars will also cool, though more slowly due to their high densities and unique internal structures. Black holes will continue to capture matter and radiation as long as sources remain available. Galaxies may merge through gravitational attraction, forming increasingly large black holes at their centers. Over extremely long intervals, gravitational interactions will alter the distribution of remnants and may eject some objects from galaxies altogether. Dark energy continues to influence these events by driving the expansion of the universe. As expansion accelerates, galaxies recede from one another at increasing speeds. Eventually, galaxies outside the local group will become unreachable because space expands faster than light can traverse the distance. This creates a cosmological horizon beyond which no new information can reach observers. Over time, the observable universe will shrink to the region gravitationally bound to the local group. Distant galaxies will fade away not due to their own dimming, but because the expansion stretches their light beyond detectable wavelengths. Thermodynamic processes also play a critical role. As energy spreads more thinly across expanding space, temperature differences diminish. Without temperature, gradients energy cannot flow efficiently, and physical processes slow dramatically. Eventually, most of the universe reaches a near uniform low energy state. This state is often described as heat death or the Big Freeze. In this scenario, matter remains, but activity becomes negligible. Motion, interaction, and structure formation fade as entropy approaches its maximum possible value. The universe becomes cold and dark, and time loses much of its traditional meaning as processes that define change slow to near zero. The presence of black holes adds complexity to this picture. Black holes dominate late-stage cosmic structure. Some may reach enormous sizes through mergers and accretion. However, Hawking radiation gradually causes black holes to evaporate. This evaporation is extremely slow for massive black holes, potentially requiring timescales far beyond ordinary comprehension. For example, a supermassive black hole at the center of a galaxy could take over 10 to the 100 years to fully evaporate. As they evaporate, black holes emit particles and radiation, slowly converting their mass back into energy dispersed across the surrounding space. When the final black holes evaporate, the universe transitions into the so-called dark era. In this era, the universe contains no stars, no black holes, and no significant energy sources. Only subatomic particles and extremely low energy radiation remain. These particles may occasionally interact, but due to the immense distances and low densities, such interactions become exceedingly rare. Over unimaginable timescales, even protons may decay if theories of proton decay prove correct. If protons decay, matter slowly disintegrates into lighter particles, further contributing to the universe's gradual dissolution. If protons do not decay, matter would still persist, but in extremely inert forms. Another possibility for the universe's end is the Big Rip scenario. This depends on the nature of dark energy. If dark energy strengthens over time, meaning that its density increases, the acceleration of the universe's expansion grows without bound. Eventually, the expansion becomes so rapid that gravitationally bound structures cannot remain intact. Galaxies would be torn apart. Solar systems would disintegrate. Planets and atoms would be separated by the growing fabric of space. In the extreme version of this scenario, even subatomic particles would be torn apart, leaving the universe in a state where space-time itself becomes disconnected. Although this scenario requires a specific type of dark energy, it remains an important theoretical possibility. Yet another theoretical scenario involves vacuum decay. The universe may exist in a metastable quantum state. If a lower energy vacuum exists, the universe could transition to it spontaneously. This transition would propagate outward at nearly the speed of light. Inside the new vacuum, physical laws could differ drastically. Particle masses, forces, and space-time geometry might change. Such an event would completely redefine the structure of the universe. Although quantum field theories allow for vacuum decay, the probability appears extremely low. Still, its existence as a theoretical possibility contributes to the range of potential cosmic endings. Cyclic universe models propose alternatives to these final scenarios. In cyclic models, the universe undergoes repeated expansions and contractions. After expanding for an extended period, the universe eventually reverses into a big crunch, collapsing into a dense state before beginning another expansion. However, current evidence indicates that expansion is accelerating rather than slowing, making cyclic models less consistent with observations. While they remain mathematically interesting, the dominant view favors continued expansion driven by dark energy. These scenarios highlight how the universe's fate depends on the behavior of dark energy, the stability of matter, the dynamics of gravity, and the influence of thermodynamics. Each model offers a different picture of the universe's distant future, but all remain grounded in known physical laws. Whether the cosmos ends in heat death, black hole evaporation, accelerated expansion, or vacuum decay, the universe's fate reflects the structure of the laws that govern it from the Big Bang to its final stages. The long-term evolution of the universe depends heavily on the physical laws that determine how matter, energy, and space-time interact. To understand how these interactions shape the cosmos over extremely long timescales, it is necessary to examine the different eras through which the universe will pass. After the current stelliferous era, characterized by active star formation and luminous galaxies, the universe gradually shifts into a period dominated by stellar remnants and dark energy. This transition marks the beginning of a slow decline in cosmic activity, driven by the exhaustion of fuel sources and the persistent expansion of space. In the far future, gravitational interactions remain influential even as luminous matter becomes scarce. Within galaxies, long-term gravitational effects cause stars and remnants to migrate through their environments. Some remnants will be drawn toward the centers of galaxies, merging with supermassive black holes. Others will be ejected into intergalactic space due to gravitational slingshot effects. The distribution of matter becomes more diffuse as expansion accelerates. Galaxy clusters that are gravitationally bound remain intact, but structures beyond local gravitational bounds move away rapidly. This separation increases as dark energy becomes more dominant relative to matter. As trillions of years pass, the proportion of matter capable of forming stars continues to diminish. Gas clouds that once fueled star formation become locked within compact remnants or dispersed beyond the reach of gravitational collapse. Stellar collisions become less frequent as objects drift farther apart. Stellar remnants such as white dwarfs cool gradually and eventually become black dwarfs, extremely cold and faint objects. These remnants emit almost no radiation and contribute to the overall cooling of the universe. Their presence marks a major shift from the energetic and dynamic early universe to a quiet and increasingly uniform state. Black holes remain among the last energetic objects in the late universe. Their gravitational influence continues long after star formation ends. Over time, black holes may merge through interactions within galaxies or clusters. The resulting larger black holes become powerful gravitational anchors. However, these objects also face eventual decay through Hawking radiation. This radiation causes black holes to lose mass slowly, though the timescales involved are enormous. As a black hole shrinks, the rate of evaporation increases, eventually leading to a final energetic burst as the black hole vanishes completely. After the last black hole evaporates, the universe enters a phase without significant gravitational engines or compact energy sources. The thermodynamic evolution of the universe also provides important insight into its distant fate. As entropy increases, physical processes become less efficient. Heat spreads evenly throughout space, and temperature differences that drive motion and structure formation diminish. The universe moves closer to thermal equilibrium with each stage of its evolution. In the limit of maximum entropy, the universe reaches heat death, a state in which no usable energy remains to perform work. Although matter may still exist in various forms, the absence of energy gradients means that almost no physical processes can occur. This state represents one of the most widely accepted predictions for the universe's ultimate end. On even longer timescales, the stability of matter becomes relevant. Dale. Some theories propose that protons may eventually decay into lighter particles. Proton decay has not been observed experimentally, but is predicted by certain grand unified theories. If protons decay, matter slowly disintegrates over immense periods, converting the remaining baryonic material into radiation and subatomic particles. This process would further accelerate the approach to a cold and diffuse universe. The decay of matter would leave behind a sparse mixture of photons, neutrinos, and extremely low-energy particles. If protons do not decay, matter would remain indefinitely, but in inert and isolated forms. Other theoretical models propose different mechanisms for the universe's end. One scenario is the Big Crunch, in which the expansion of the universe slows and reverses. Gravity would eventually stop the expansion and cause all matter to collapse inward. This collapse would end with the universe returning to an extremely dense and hot state. However, the observation of accelerated expansion suggests that this scenario is unlikely. The current evidence indicates that dark energy will continue to drive expansion rather than allowing gravitational collapse to dominate. Cyclic models expand on the idea of the Big Crunch by suggesting that the universe undergoes repeated cycles of expansion and contraction. After collapsing into a dense state, the universe could experience another rapid expansion similar to the Big Bang. This cycle could repeat indefinitely, creating an eternal sequence of cosmic births and deaths. While mathematically interesting, these models require specific conditions in physical law, and current cosmological data favors continuous expansion rather than cyclic behavior. Vacuum decay presents another possible ending. In this scenario, the universe exists in a metastable vacuum state rather than the true lowest energy state. Transition to a lower energy vacuum would release enormous amounts of energy and alter the fundamental constants of nature. This transition would propagate at close to the speed of light and reshape the laws of physics in the affected region. If vacuum decay occurred, it could restructure or eliminate existing physical structures instantly. Although vacuum decay is a theoretically plausible scenario, current understanding suggests that the probability is extremely low on any human-relevant timescale. Another concept is the Big Rip, an outcome driven by a specific type of dark energy known as phantom energy. In this scenario, dark energy grows stronger over time. As its repulsive effect increases, it eventually overwhelms all other forces. Galaxies would be pulled apart, stars and planets would be disrupted, and ultimately even atoms could be torn apart by the accelerating expansion. Space-time would stretch at an accelerating rate until it reaches a singular end. This scenario depends heavily on the properties of dark energy, and current observations favor a more stable form. But the Big Rip remains a scientifically valid theoretical possibility. Across all these scenarios, a common theme emerges. The ultimate fate of the universe is tied to the behavior of dark energy, the stability of matter, the nature of quantum fields, and the laws of thermodynamics. Whether the universe ends through expansion, decay, collapse, or thermal equilibrium, each possibility reflects the consistent and predictable structure of the physical laws that govern it. The distant future remains beyond direct observation. Yet scientific models allow us to construct plausible pathways based on current understanding. As the universe marches into deeper epochs of time, its fate becomes shaped not by the energetic processes that once defined galaxies and stars, but by subtle interactions that unfold slowly across unimaginable durations. To gain a clearer understanding of how the cosmos may approach its final moments, it is helpful to examine individual components of the universe separately, allowing each aspect of physics to reveal its contribution to the long-term transformation of reality. Viewing the distant future through these layered perspectives creates a calmer and more organized picture of cosmic evolution, offering a soothing journey through the science of endings. One useful perspective begins with the future of radiation. In the early universe, radiation dominated over matter, but in the distant future, radiation becomes stretched by expansion until its wavelengths grow extremely long. These low-energy photons drift through space with almost no interactions. Their presence creates a faint background that cools gradually toward absolute zero. This quiet radiation field acts as a kind of cosmic whisper, an echo of ancient stars whose light has been stretched into stillness by the expansion of space. Another perspective involves the motion of particles. As expansion continues, particles become separated by growing distances. Collisions become rare, and the universe transitions into a state where particles move without interruption for vast periods. This change reflects a shift from a dynamic environment filled with interactions to a tranquil cosmic landscape where motion continues but almost nothing disturbs it. The universe becomes a place where silence, rather than energy, defines the flow of time. The study of cosmic structure offers another view of the universe's future. Gravity once shaped galaxies into spirals, clusters, and filaments. Over long durations, gravitational structures reach a form of quiet stability. If one imagines drifting through these isolated regions in the far future, the experience would resemble floating within a peaceful emptiness, disturbed only by the occasional presence of a dark remnant or a wandering particle. The universe becomes a serene environment shaped more by absence than presence. The evolution of black holes continues to fascinate scientists studying the universe's end. Stephen Hawking's prediction of black hole evaporation introduced the idea that nothing remains eternally unchanged. Even the most massive black holes gradually lose mass through quantum processes. While this evaporation is incredibly slow, the concept itself is calming in its own way. It shows that even the densest and most powerful structures eventually release their energy, returning it gently to the universe over long spans of time. The end of black holes symbolizes the universe's slow transformation toward simpler states, each step unfolding without haste. Another dimension of the universe's future involves dark matter. Although dark matter does not interact strongly with light, its gravitational influence shapes cosmic structure. As galaxies separate, dark matter halos drift apart as well. They remain invisible, but continue to sculpt the gravitational landscape. In the far future, these halos become faint shadows of cosmic architecture, quiet reminders of the universe's earlier complexity. Their persistence contributes to the slow calming of the universe as gravitational interactions weaken over time. Dark energy influences cosmic fate at an even deeper level. If dark energy remains constant, the expansion continues indefinitely, guiding the universe toward a quiet and cold ending. If it strengthens over time, it may lead to more dramatic outcomes, such as the tearing of gravitational structures. Regardless of the path dark energy takes, its presence ensures that the universe gradually enters a more diffuse and silent state. The expansion becomes a kind of cosmic breath, slowly drawing matter apart and replacing activity with stillness. Scientific perspectives also draw from the work of researchers such as Roger Penrose, who explored the idea of conformal cyclic cosmology. In his view, the universe's end may connect smoothly to a new beginning through mathematical structures that compress infinite time into a final transformation. This concept, while speculative, adds depth to the discussion. It introduces the idea that endings may resemble transitions rather than abrupt terminations. Penrose's work contributes a sense of continuity that softens the notion of cosmic finality and encourages reflection on the cyclical nature of existence. Another calming perspective comes from considering how quiet the universe becomes. As temperatures drop and interactions fade, the universe reaches a state where change occurs so slowly that time itself feels stretched. This slow fading is gentle rather than violent. Instead of sudden collapse or explosive transformation, the far future unfolds like a deep cosmic sleep. Energy spreads thinly, particles drift without disturbance, and space expands with steady patience. The universe becomes a tranquil environment governed by processes that operate on scales far beyond human imagination. Quantum fluctuations add yet another layer of subtlety. Even in a universe approaching stillness, quantum fields continue to fluctuate at extremely small scales. These fluctuations introduce momentary variations in energy and position, offering a reminder that motion never fully disappears. These tiny vibrations create a soft foundation beneath the quiet cosmic landscape, like the faint hum of an unseen engine that persists even in the deepest silence. The presence of quantum fluctuations provides a gentle continuity that persists even when the universe appears almost perfectly calm. Throughout all these scenarios, whether involving heat death, black hole evaporation, or speculative transformations, a unifying theme emerges. The universe's end is not a single event, but a long sequence of transitions shaped by natural laws that operate consistently across time. These transitions occur gradually, with each stage blending smoothly into the next. The future of the universe unfolds through calm processes rather than abrupt ones, allowing the cosmos to drift slowly into its final state. As the universe drifts into deeper cosmic time, its evolution becomes influenced not by the energetic processes that once shaped galaxies and stars, but by much gentler mechanisms that unfold slowly across vast stretches of history. One of the most effective ways to understand this distant future is to separate the universe into its fundamental components and examine how each one behaves when energy, structure, and motion begin to fade. This approach reveals a picture of the cosmos that becomes increasingly quiet and delicate, like a vast landscape settling gradually into a deep cosmic rest. The first component to consider is the behavior of light. In the early stages of cosmic history, photons carried energy across space with relative ease. As expansion accelerates, however, light becomes stretched into longer wavelengths, losing energy as it travels. Over time, the cosmic background radiation cools and fades. The universe becomes filled with extremely soft and low-energy radiation, so faint that it drifts almost unnoticed through expanding space. These long wavelength photons act like a gentle background whisper, a final echo of the once bright and active cosmos. Another important component involves the fate of stars and their remnants. During the Stelliferous era, stars burned brightly, producing warmth and structure. Yet as trillions of years pass, stars exhaust their nuclear fuel. White dwarfs cool into black dwarfs. Neutron stars lose heat and fade. Even planets, which once orbited in warm and energetic systems, drift through cold and empty regions. These remnants persist for long durations, but their presence shifts from dynamic to silent. Imagine wandering through such an era. Instead of fiery suns and glowing nebulae, the universe contains only quiet, cold remnants scattered across expanding space. Black holes introduce a different type of evolution. They remain among the last powerful structures. Their gravity continues to shape their surroundings. Yet, according to Hawking radiation, they evaporate slowly. This evaporation process is extremely gentle, almost like a slow release of stored energy. Over unimaginable timescales, black holes shrink and eventually vanish. The final moments of each black hole mark the end of a region's last major energy source. After the last black hole evaporates, the universe enters a tranquil phase in which compact, massive structures no longer exist. Dark matter adds another dimension to the universe's distant future. Although dark matter does not emit or absorb light, its gravitational presence shapes the formation and evolution of galaxies. In the distant future, dark matter halos remain as invisible frameworks surrounding the last remnants of structure. These halos drift apart as expansion continues, becoming silent outlines of the cosmic architecture that once existed. Their persistence gives the universe a quiet and ghost-like structure, defined not by brilliant light, but by the faint memory of gravitational patterns. Dark energy plays an even more fundamental role. If dark energy remains constant, the universe expands forever. Structures separate until they become isolated, and each gravitationally bound region becomes an island in the expanding sea of space. The night sky in such an era would appear nearly empty. Distant galaxies vanish beyond the cosmic horizon as their light becomes infinitely redshifted. What remains is a peaceful but lonely region containing only the remnants that expansion cannot overcome. If dark energy grows stronger over time, the universe may face more extreme outcomes, such as the Big Rip. Yet even this scenario unfolds gradually, beginning with the gentle stretching of space and leading eventually to the disruption of structures. Scientific perspectives also draw from the work of researchers such as Freeman Dyson, who explored how intelligent life might persist in a cooling universe. Dyson proposed that life could adapt by slowing its processes, stretching thoughts and actions across enormous time intervals. Although speculative, this idea introduces a soothing perspective. It suggests that intelligence, if present, could match the universe's pace. As physical processes slow, consciousness could slow with them, entering a long and peaceful rhythm that mirrors the universe itself. Another angle comes from examining the flow of time. As temperature drops and processes slow, time becomes less meaningful. Many of the events that once defined cosmic evolution occur less frequently or cease entirely. For an observer, drifting through the distant future, time might feel extended, almost stretched into a gentle continuum where change occurs so slowly that it blends into the background. This slow unfolding creates a calming picture of the universe, one in which endings are not abrupt but gradual, like the final notes of a long and soothing melody. Quantum fluctuations add subtle activity to this quiet environment. Even in a universe approaching near absolute stillness, quantum fields continue to fluctuate in gentle rhythms. These fluctuations are incredibly small, yet they persist as a fundamental feature of spacetime. They act like faint vibrations beneath the calm surface of reality, giving the universe a quiet undercurrent of motion. This persistence provides a comforting sense of continuity. Even as large-scale structures fade, quantum processes remain active, ensuring that the universe never becomes entirely static. Researchers such as Andrei Lind have discussed multiverse models that allow the universe to continue in different forms even as one region fades. In these models, new universes may emerge through inflationary processes driven by quantum fluctuations. Although these ideas remain speculative, they offer gentle conceptual pathways through which cosmic endings transition into new beginnings. Such models suggest that the universe's final state may not be an absolute end, but part of a broader cosmic landscape shaped by ever-evolving regions of space-time. Throughout this journey, one theme remains constant. The universe approaches its end, not through sudden destruction, but through gradual and gentle transformation. Energy spreads out softly. Structures dissolve slowly. Expansion continues with quiet persistence. Quantum fluctuations hum beneath the surface. Matter cools and separates. In this long and peaceful evolution, the universe drifts toward a calm and timeless state shaped by the same laws that guided its birth and growth. As the universe moves beyond the eras, we can easily imagine it begins to enter regions of time so vast that ordinary measurements lose meaning. To explore these distant phases more clearly, we can divide the far future into conceptual domains, each shaped by a different set of physical processes. This layered approach helps reveal how the universe gradually shifts from a realm of active structure to one of ever-deepening tranquility. The vastness of these timescales can feel overwhelming, yet when viewed gently, the slow fading of cosmic activity carries a calming rhythm, like the steady dimming of a light that slowly guides the universe into rest. One domain to examine is the future of chemical elements. In the early universe, elements formed through fusion in stars, and during the first few minutes after the Big Bang. Over long durations, chemical complexity declines. Heavy elements become locked inside stellar remnants and star-forming regions disappear. As expansion continues, atoms drift farther apart, and chemical reactions become nearly impossible. The universe becomes chemically quiet, a place where molecules no longer form and existing structures remain unchanged for unimaginable periods. This chemical stillness creates a cosmic environment defined by slow continuity rather than transformation. Another domain involves gravitational structure. In the present universe, gravity sculpts galaxies, clusters, and large-scale filaments. But in the distant future, these structures lose their coherence. Internal interactions remain, yet the broader cosmic web dissolves as expansion draws distant regions apart. Within gravitationally bound systems, remnants continue orbiting each other, but these motions slow as energy is exchanged over long durations. Eventually, many remnants are ejected through gravitational encounters, leaving behind smaller and quieter systems. This long-term gravitational evolution carries a peaceful tone, like the slow shifting of particles in a settling fluid. The fate of black dwarfs introduces a new layer of cosmic transformation. Black dwarfs, the cooled remains of once bright stars, may undergo exotic processes over unimaginable timescales. Some theoretical predictions suggest that quantum tunneling may eventually allow carbon nuclei inside black dwarfs to fuse, producing extremely faint bursts of energy. These events are not destructive, but subtle, a final exhale of stellar matter after an eternity of calm. Astrophysicists such as Ethan Siegel have described these as the universe's last flickers of starlight. These events, if they occur, would be rare, quiet, and gentle, appearing as small flashes in an otherwise dark cosmos. A different perspective arises when considering dark matter and its long-term behavior. Although dark matter does not interact electromagnetically, it participates in gravitational dynamics. In the far future, dark matter halos become faint gravitational shells around isolated regions. Their influence persists even when visible matter fades. These halos maintain structure silently, like invisible sculptures suspended in space. Over time, their significance becomes symbolic rather than dynamic. They serve as reminders of the universe's earlier complexity, while contributing to the quiet stability of its distant future. Dark energy's influence remains one of the deepest factors shaping the universe's fate. The smooth and steady pressure of dark energy pushes galaxies apart with a calm but unrelenting force. This force creates expanding domains of silence where light from distant regions can no longer reach observers. The observable universe shrinks, not because space itself is collapsing, but because distant light stretches into wavelengths too long to detect. This produces a softening of the cosmic landscape, a gradual dimming that guides the universe toward isolation. The effect feels less like destruction and more like a gentle withdrawal, a cosmic curtain closing slowly over billions of years. The expansion of space-time also affects the passage of time itself. In the distant future, processes occur so slowly that time feels elongated. A single interaction between particles may require intervals far longer than the current age of the universe. This slowing of activity produces a deep sense of calm. The universe moves so gently that change becomes almost imperceptible. This near timeless state is one of the defining features of the far future, and it provides a soothing perspective on the nature of cosmic endings. Instead of an abrupt conclusion, the universe enters a slow and peaceful drift. Quantum mechanics continues to play a role even in this quiet era. Quantum fields fluctuate with delicate variations that occur everywhere in space. These fluctuations produce tiny pulses of energy that persist even when the universe is cold and nearly empty. The presence of these fluctuations ensures that the universe never becomes fully static. They act like the faint hum of a hidden engine that continues turning even when all larger mechanisms have stopped. For some researchers, including those exploring the foundations of quantum field theory, these fluctuations suggest that the deep structure of space-time retains a subtle vibrancy, no matter how quiet the universe becomes. Vacuum stability is another domain worth considering. Physicists such as Sidney Coleman discussed how a metastable vacuum could theoretically transition into a more stable one. While current estimations suggest that our vacuum is long-lived, The idea that the universe contains hidden layers of potential still adds richness to the discussion. Vacuum decay, if it were to happen, would occur quietly at first, forming a small region that expands rapidly. The transition would not be violent from the perspective of the cosmos, because it would simply replace one form of stability with another. This view provides a strangely serene interpretation of a dramatic event, reframing it as a natural quantum transition rather than a destructive end. Another perspective comes from cosmological horizon physics. As expansion accelerates, each observer becomes surrounded by a shrinking sphere of visibility. This cosmic horizon behaves like a boundary beyond which events become permanently inaccessible. Over time, the horizon creates an environment similar to an isolated island in an endless ocean. This isolation brings a sense of stillness. Each region becomes self-contained and evolves independently. Inside these regions, the universe becomes a calm space defined by very slow processes and extremely rare interactions, aligning perfectly with the gentle tone of a cosmic end. Even more speculative ideas, such as the Poincaré recurrence theorem, introduce thought-provoking possibilities. This theorem suggests that in some systems, states can theoretically recur given enough time. However, in an expanding universe, recurrence becomes extremely unlikely. Instead, the universe drifts toward a state where new events no longer occur. This absence of recurrence reinforces the sense that the universe's fate is not cyclic, but softly terminal, unfolding in one direction toward increasing calm. When all these domains are combined, a unified picture emerges. The universe does not end suddenly, violently, or chaotically. Instead, it transitions slowly through stages of cooling, expanding, quieting, and fading. Structures dissolve gradually. Energy thins gently. Space grows wider and more silent. Quantum fields whisper softly beneath the surface, and time stretches into a long, soothing continuum. The universe approaches its end like a vast and peaceful exhale, guided by the same physical laws that shaped its birth and growth. The long-term fate of the universe becomes clearer when each potential end scenario is examined through the combined lenses of cosmology, quantum theory, and thermodynamics. As the universe evolves through trillions, quadrillions, and eventually unimaginable numbers of years, the physical processes that once shaped galaxies and stars slow to almost complete stillness. To understand how these processes lead to the end of cosmic activity, it is necessary to examine the underlying mechanisms that govern matter and energy in extreme conditions. Each scenario, whether heat death, vacuum decay, the Big Rip, or a far more subtle thermodynamic ending, emerges from the behavior of the universe's most fundamental components. One of the dominant ideas in scientific literature is the heat-death scenario. Heat death arises from the second law of thermodynamics, which states that entropy must increase in a closed system. Over time, energy spreads more evenly across space, reducing temperature differences. These differences are essential for performing work and driving physical processes. The universe began in a hot, low entropy state, but it gradually approaches a cold, high entropy state as energy disperses and structures dissolve. As dark energy accelerates the expansion of space, energy becomes more thinly distributed. Eventually, conditions approach uniformity, with no meaningful gradients remaining. In this environment, physical processes can continue only at extremely slow rates, eventually approaching a halt. This state represents the classical form of cosmic heat death. Another important idea involves the long-term stability of subatomic particles. The universe's distant future depends significantly on whether protons are stable or decay over extreme timescales. If protons decay, matter itself gradually dissolves into radiation and lighter particles. Proton decay has not been observed, but some grand unified theories predict that protons may decay over timescales far exceeding the current age of the universe. If this occurs, the material universe transitions toward a state dominated by photons, neutrinos, and other stable particles. Even without proton decay, matter becomes increasingly isolated due to expansion, eventually leading to a universe composed of inert remnants and low-energy radiation. Black hole evaporation is another cornerstone of long-term cosmic evolution. According to Hawking radiation theory, black holes emit particles due to quantum effects near their event horizons. This radiation slowly reduces their mass. Small black holes evaporate faster, while supermassive black holes take far longer. The largest black holes may take up to 10 to the power of 100 years to fully evaporate. During evaporation, black holes convert their mass into energy. After the final evaporation, the universe loses its last major energy-generating structures. With no remaining black holes, the cosmos enters a stage dominated by extremely low-energy particles and sparse radiation. Dark energy plays a crucial role in shaping cosmic destiny. Current observations indicate that dark energy is constant, or nearly constant, over time. This leads to a scenario called the Big Freeze, in which the universe expands indefinitely. Galaxies move beyond each other's observable horizons, and the universe becomes divided into isolated regions. Each region eventually contains only the remnants of local gravitational structures. As expansion continues, wavelengths of light stretch, causing radiation to redshift into extremely low energy states. Over time, the observable universe within any region becomes darker and quieter as structures recede beyond reach. However, the nature of dark energy is not fully understood. If dark energy strengthens over time, the universe could face the Big Rip. In this extreme scenario, the expansion becomes so strong that it tears apart gravitationally bound structures. First, galaxy clusters separate, then galaxies disintegrate, followed by the disruption of star systems. Eventually, the expansion becomes powerful enough to overwhelm electromagnetic forces, leading to the breakdown of atoms. Even subatomic particles could be torn apart as space-time expands rapidly toward an ultimate singular end. This scenario requires a specific equation of state for dark energy, and although current measurements do not favor it, the possibility remains open within theoretical physics. Vacuum decay offers a radically different type of cosmic ending. Quantum field theory suggests that the universe may reside in a metastable vacuum state, not the true minimum energy state of the field. If a lower energy state exists, the universe could undergo a transition into this deeper vacuum. Such a transition would create a bubble of the new vacuum that expands outward at nearly the speed of light. Inside this bubble, the laws of physics could differ significantly. Particle masses, interaction strengths, and even the structure of spacetime could change. Such a transition would be catastrophic for existing structures, eliminating them instantly. While vacuum decay is theoretically possible, the probability appears extremely low over any human-relevant timescale. Cyclic and oscillatory models provide alternative viewpoints. Some theories propose that the universe undergoes cycles of expansion and contraction. In these models, the Big Bang is not the absolute beginning, but part of an eternal sequence. After expanding for trillions of years, the universe might reverse its expansion and collapse in a big crunch. This collapse could then trigger another expansion. However, modern observations of accelerated expansion make this scenario unlikely. The influence of dark energy suggests that expansion will not reverse. Another important concept involves gravitational clustering in the very distant future. Even as expansion drives galaxies apart, gravitational interactions continue to shape the matter that remains within isolated regions. Over long timescales, some remnants may form stable structures, while others drift through increasingly empty space. These structures continue to cool until they approach thermodynamic inactivity. The universe becomes a vast and essentially static environment with extremely slow changing conditions, governed primarily by quantum effects and extremely low energy processes. Quantum tunneling and rare events may also influence cosmic endings in unexpected ways. Over incomprehensible timescales, quantum tunneling could allow particles to escape gravitational wells or produce rare interactions that slowly alter the distribution of matter. Although these processes occur extremely rarely, the timescales involved in the universe's fate allow even the rarest events to contribute to long-term evolution. These quantum effects emphasize that the universe's distant future is shaped not only by classical physics, but also by subtle quantum mechanical processes. Regardless of the specific ending scenario, the ultimate fate of the universe highlights the deep connection between cosmic evolution and fundamental physics. Whether the universe ends in heat death, decay, disintegration, or a dramatic transformation, each possibility reflects stable and consistent laws. The internal structure of physical law governs every stage of cosmic history, from the earliest moments after the Big Bang to the unimaginable timescales of its final era. Although humans will never witness these distant stages, scientific models allow the construction of coherent and physically consistent predictions that reveal the long arc of cosmic destiny. As the universe progresses into its distant eras, the distribution of matter, energy, and space-time becomes increasingly governed by processes that occur on extremely long timescales. To understand these eras, it is helpful to break them into conceptual stages, each defined by the dominant physical processes at work. These stages reveal a gradual and predictable decline in cosmic activity as temperature drops, expansion accelerates, and energy becomes more uniformly dispersed. Although the details of each era depend on the behavior of dark energy and the stability of matter, the overall direction of cosmic evolution remains aligned with thermodynamic and quantum principles. The stelliferous era, in which stars actively form and shine, eventually transitions into the degenerate era (DY). During this period, the universe becomes dominated by remnants of stellar evolution, including white dwarfs, neutron stars, and black holes. White dwarfs gradually cool as they radiate away their residual heat. Over trillions of years, they become cold black dwarfs, dark and inert. Neutron stars, although extremely dense, also cool slowly until thermal radiation becomes negligible. These evolutionary pathways reflect the diminishing availability of nuclear fuel in the universe and the irreversible decline in star formation as available gas becomes locked within remnants or dispersed across expanding space. Galactic dynamics continue to evolve throughout these distant eras. Within gravitationally bound regions such as galaxy clusters, remnants continue to interact through gravitational influences. Some remnants may collide or merge due to long-term orbital decay or perturbations. Others may be ejected from their host galaxies through gravitational slingshot events. These ejections send objects drifting through intergalactic space, eventually becoming isolated as expansion accelerates. Over time, most galaxies lose their coherent structure, leaving behind sparse distributions of remnants within gravitationally stable regions. As the influence of dark energy strengthens, the expansion of the universe accelerates further. Regions not gravitationally bound become permanently separated. The observable horizon contracts relative to distant galaxies as their light becomes increasingly redshifted. Eventually, only structures within local gravitational wells remain visible. This isolation marks a profound shift in the universe's large-scale appearance. Instead of a sky filled with galaxies, the cosmic future contains only the remnants of a single gravitationally bound region. This separation is permanent due to the expansion of space-time exceeding the speed at which light can travel across the ever-increasing distances. The thermodynamic implications of this expanding universe are significant. Energy becomes more spread out and available energy declines. Without temperature gradients, no processes can occur that require work. In the heat death scenario, the universe approaches maximum entropy, a state in which all energy is uniformly distributed. Even if matter persists in some form, the absence of gradients prevents meaningful interactions. Heat death, therefore, describes not a violent ending, but a slow transition into quiet equilibrium. The universe becomes cold, dark, and nearly motionless. Black holes remain important for a very long time. They represent concentrated energy and remain active through the accretion of matter and gravitational influence. Over immense timescales, black holes dominate the energy landscape of the universe. However, Hawking radiation predicts that black holes gradually lose mass through quantum processes at their event horizons. The rate of evaporation is extremely slow for large black holes, but as they lose mass, the evaporation accelerates. Eventually, even the largest black holes evaporate entirely, releasing their energy into the universe as radiation. After the final black hole evaporates, no significant gravitational engines remain. This transition marks the beginning of the dark era. During the dark era, the universe contains mostly subatomic particles, low-energy photons, neutrinos, and potentially stable remnants of matter. These particles drift through ever-expanding space with extremely low densities. Due to the vast distances between particles and the extremely low temperatures, interactions become exceedingly rare. If proton decay occurs, matter gradually disintegrates over immense timescales, further reducing the complexity of the universe. Even without proton decay, the ever-expanding space ensures that matter becomes isolated to the point of near-complete inactivity. Beyond these classical scenarios, more speculative possibilities arise. Vacuum decay remains one such possibility. If the universe resides in a metastable vacuum state, it could transition to a lower energy configuration. This transition would fundamentally alter the structure of the universe. The new vacuum would propagate as a bubble expanding at nearly the speed of light. Inside this bubble, the laws of physics could differ in ways that prevent the continued existence of familiar structures. Although unlikely, vacuum decay demonstrates how quantum processes could abruptly reshape the cosmic future. Another possibility arises from the idea that dark energy could evolve over time. If dark energy increases its density, even slightly, it could lead to the Big Rip. In this extreme scenario, expansion overwhelms gravity, electromagnetism, and eventually the strong nuclear force. Structures at every scale become vulnerable to the accelerating expansion. First, galaxies are torn apart, then stars, planets, molecules, and finally atomic nuclei. If dark energy evolves in this way, the universe ends in a dramatic and highly energetic disintegration, driven by runaway expansion. Cyclic models present an alternate picture. In these theories, the universe transitions through repeated phases of expansion and contraction. After a long period of expansion, the universe may reverse direction, collapsing into a dense and hot state known as the Big Crunch. This collapse could then initiate another expansion, producing a new cycle. Although mathematically consistent, these models require specific conditions that do not align with current observations of accelerating expansion. However, they remain of theoretical interest because they offer a universe without a singular endpoint. A more subtle scenario involves the possibility that the universe does not end in a single event, but transitions into a state of minimal energy, where physical processes occur so slowly that time itself becomes difficult to define. In this view, the universe does not end in destruction or collapse, but in stagnation. This slow fade into inactivity reflects the relentless increase of entropy and the diminishing availability of usable energy. The universe becomes a quiet and almost timeless environment, dominated by quantum fluctuations and extremely rare events. Throughout all these possibilities, one consistent theme emerges. The ultimate fate of the universe is controlled by the fundamental physical laws that govern its evolution. These laws determine how matter decays, how energy disperses, how space-time expands, and how entropy evolves. Whether the universe ends in heat death, vacuum decay, the Big Rip, or a slow thermodynamic fading. The outcome reflects the deep and unchanging structure of physical law. The end of the universe may be distant beyond comprehension, yet the scientific frameworks used to understand it reveal the elegance and consistency of the cosmos from its earliest moments to its far future. As the universe continues its progression into deeper cosmic time, the interaction between gravity, quantum processes, and the accelerating expansion of space becomes increasingly subtle. Each mechanism that once shaped galaxies and stellar evolution loses influence as energy becomes more diffuse and structures grow increasingly isolated. Understanding the end of the universe requires tracing these processes across unimaginably long timescales and examining the behavior of matter and energy when nearly all macroscopic activity has ceased. In this distant future, the universe becomes governed by the slowest and weakest processes in nature, allowing theoretical predictions to be built on the foundations of thermodynamics, quantum field theory, and general relativity. During the transition from the degenerate era to the far later cosmic stages, the distribution of stellar remnants changes dramatically. Gravitational interactions slowly reorder the positions of white dwarfs, neutron stars, and black holes within gravitationally bound regions. Over exceedingly long times, many remnants collide or merge, although such events become rarer as expansion increases the distances between structures. Within galaxies, gravitational friction, orbital decay, and chaotic interactions eventually guide many remnants towards central supermassive black holes. These black holes grow gradually as they consume nearby material, yet the overall availability of matter continues to decline as the universe expands and star formation ceases entirely. Black holes represent one of the last sources of significant energy release, even as their activity diminishes. The process of Hawking radiation predicts that black holes emit particles due to quantum fluctuations near their event horizons. Larger black holes evaporate more slowly, but all black holes lose mass over time. The evaporation of supermassive black holes marks the end of the last major gravitational engines in the universe. As each black hole evaporates the energy, it releases spreads across expanding space, gradually diluting into an ever colder environment. When the final black holes evaporate, the universe enters a phase devoid of compact, massive structures. Thermodynamic factors continue to shape the universe throughout these transitions. The second law of thermodynamics requires entropy to increase, gradually driving the universe toward a state of maximal disorder. In practical terms, this means that all energy gradients, which once powered stars and planetary systems, fade over time. Heat spreads uniformly, and the temperature approaches an extremely low but non-zero value. As entropy rises, the ability of the universe to sustain complex processes declines. Motion slows, interactions weaken, and structure formation becomes impossible. This gradual slide toward uniformity is one of the defining features of the heat death scenario. However, thermodynamic processes alone do not define the universe's ultimate fate. Quantum mechanics also plays a crucial role, especially in the extremely distant future. Quantum tunneling allows particles to move through energy barriers that they cannot overcome classically. Although the probability is small, over immense timescales, tunneling may allow bound particles to escape their structures. Even within black dwarfs, neutron stars, and other remnants, quantum tunneling could slowly rearrange matter and release small amounts of energy. These processes occur with such low probability that they have negligible impact in the near future, yet over cosmic timescales they contribute to the slow disassembly of matter. The stability of matter becomes increasingly important. If protons decay, matter will gradually dissolve into radiation and lighter particles. Proton decay times predicted by some theoretical models are tremendously long, far exceeding the current age of the universe. Even if protons decay extremely slowly, the universe's far future becomes dominated by particles that cannot form complex structures. Over immense durations, the universe transitions from one filled with stars and galaxies to one composed primarily of low-energy photons, neutrinos, and extremely sparse particles drifting through dark, expanding space. If protons are stable, matter persists, but its isolation increases to the point where interactions become virtually non-existent. The role of dark energy continues throughout these stages. Current observations suggest that dark energy remains roughly constant over time, driving the Big Freeze scenario, in which the universe expands forever. Galaxies beyond gravitationally bound regions vanish beyond the observable horizon as their light becomes infinitely redshifted. Eventually, the observable universe shrinks to a small region surrounding the observer, containing only local gravitationally bound remnants. With time, even these remnants cool into inert structures. The accelerated expansion ensures that no new matter enters the observable region, leaving a cosmic landscape dominated by isolation and stillness. More extreme possibilities depend on the behavior of dark energy. If dark energy increases with time, the universe may undergo the Big Rip, in which accelerating expansion eventually overcomes all forces. Structures at every scale would be torn apart. Galaxies would dissolve as expanding space overwhelms gravity. Planetary systems would separate as stellar remnants drift apart. Eventually, even atomic nuclei would be torn apart by space-time expansion. The universe would reach a singular event where space-time becomes disconnected. This scenario requires a particular equation of state for dark energy, and while current measurements do not strongly support it, the Big Rip remains an important theoretical possibility. Vacuum decay presents an entirely different mechanism for cosmic destruction. In quantum field theory, the universe may be trapped in a false vacuum, a metastable state with higher energy than the true vacuum. If tunneling into the true vacuum occurs, a bubble of new vacuum would form and expand at nearly the speed of light. Within this bubble, physical laws could differ drastically. Particle masses, fundamental forces, and even the geometry of space-time could change. Existing structures would be destroyed instantly as the bubble passes through. Although this possibility is theoretically allowed, current models suggest that the probability is low. Nevertheless, vacuum decay remains part of the scientifically legitimate discussion surrounding cosmic endings. Even more subtle possibilities exist within the realm of quantum gravity. Some theories propose that space-time may not extend indefinitely, but could transition into new forms at extremely low energy scales. Others suggest that the universe may undergo a form of quantum recurrence in which states repeat over extraordinarily long cycles. While highly speculative, these ideas highlight the deep uncertainties involved in predicting the extremely far future. They demonstrate that the ultimate fate of the universe depends not only on known physics, but also on aspects of physical law that remain poorly understood. Despite these uncertainties, one overarching concept remains consistent across theories. The universe's end is governed by the interplay between expansion, entropy, quantum processes, and the long-term behavior of fundamental forces. Whether the universe ends through heat death, vacuum decay, or a radical transformation driven by changing dark energy, the outcome reflects the same laws that have guided cosmic evolution since the Big Bang. These laws shape everything from the formation of galaxies to the evaporation of black holes, creating a coherent pathway from the universe's beginning to its distant future. As we move deeper into the distant future of the universe, the processes that once defined cosmic evolution fade into subtle variations of silence and emptiness. At this stage, the universe resembles a vast ocean of space stretching in all directions, filled not with galaxies or stars, but with sparse particles drifting without urgency. To understand this profound quiet, it is useful to examine specific themes that emerge only when most familiar structures have disappeared. Each theme opens its own window into the cosmic future, revealing an environment shaped by slow decay, gentle expansion, and the lingering echoes of earlier eras. One theme concerns the ultimate fate of temperature. In the present universe, temperature varies widely from stellar cores to interstellar clouds. Yet as time passes, temperature differences diminish. Radiation cools as wavelengths stretch. Even the residual warmth of stellar remnants fades. Over extraordinary times, the universe approaches a uniform temperature hovering just above absolute zero. This convergence occurs gradually and silently. It transforms the universe into a nearly isothermal expanse where thermal motion becomes gentle and rare. The universe settles into a soft equilibrium, a thermodynamic stillness that defines the heat-death scenario. Another theme arises from the study of gravitational relaxation. In gravitational systems, interactions occur over long durations as objects exchange energy through slow orbital processes. In the early stages of cosmic history, these interactions shaped galaxies and clusters. In the far future, gravitational relaxation becomes one of the last active mechanisms. Remnants drift through their gravitational wells with diminishing interactions. Occasionally, two remnants may pass close enough to exchange momentum, sending one object outward into intergalactic space while the other sinks deeper into the gravitational core. These interactions become less common as expansion separates structures, but they continue to influence the slow settling of matter. The concept of isolation becomes more important as expansion accelerates. Each gravitationally bound region becomes effectively cut off from the rest of the universe. Galaxies beyond these regions pass beyond the cosmic horizon. Light from them becomes stretched into wavelengths too long to detect. Over time, an observer would see fewer and fewer objects in the sky until only the local remnants remain. This process is not abrupt, but gradual. It resembles the fading of distant lights over an immeasurably long night. The isolation created by the horizon produces a deep sense of cosmic solitude, one that aligns with the quiet, calming tone of the universe's far future. The behavior of subatomic particles also becomes essential to understanding the universe's end. If protons decay, matter slowly dissolves into lighter particles, such as positrons, neutrinos, and low-energy photons. This decay unfolds with a softness that matches the universe's gradual cooling. The slow disintegration of matter does not create bursts of energy or violence. Instead, it releases small amounts of energy into expanding space, further contributing to the universe's drift toward uniformity. If protons do not decay, matter remains, but interactions become exceedingly rare as distances increase and temperatures drop. A more nuanced theme involves the evolution of quantum states in an almost empty universe. Quantum fields never become fully silent. They produce fluctuations of energy that appear spontaneously and vanish just as quickly. These fluctuations continue even when the universe is cold and nearly empty. In the far future, quantum fluctuations create gentle ripples across space-time, subtle and persistent. These ripples do not lead to new structures or energetic processes, but they maintain a quiet foundation beneath the universe's stillness. Some researchers describe this as the quantum breathing of the cosmos, a soft and continuous rhythm that remains even after large-scale structure fades. Another area of interest is the fate of dark energy in the long term. If dark energy remains constant, the universe expands forever with steady acceleration. If dark energy evolves, its behavior could lead to very different outcomes. Some theoretical models predict a gradual decay of dark energy into another form of energy or matter. Others suggest that dark energy could strengthen over time, producing the Big Rip. Although these models remain speculative, they highlight how the ultimate fate of the universe depends on the nature of the mysterious force driving its expansion. Observations continue to refine our understanding of dark energy, yet the extremely long timescales involved ensure that its long-term behavior remains uncertain. A fascinating perspective comes from the study of information. Physicist John Wheeler famously stated that reality may be rooted in information, suggesting that the universe evolves through the transformation and dispersal of information across space-time. In the far future, information becomes increasingly diluted. As structures decay and energy spreads, the information encoded in stars, galaxies, and atomic arrangements becomes less accessible. Over time, information disperses so widely that reconstructing the past becomes impossible. This aligns with the heat death scenario in which entropy reaches a maximum and information becomes nearly uniform. The universe becomes a quiet archive in which almost all details of earlier eras have been erased by expansion and decay. Another theme emerges from the concept of cosmic memory. Even as structures vanish, the universe retains subtle records of its evolution. Long wavelength radiation remains as an echo of earlier temperatures. Sparse particles carry traces of their interactions. Quantum fluctuations preserve faint patterns in fields. Although these forms of memory are extremely subtle, they create a sense that the universe retains a soft imprint of its past, even as it moves toward silence. These lingering imprints contribute to a gentle continuity across cosmic history. The role of scientific imagination also becomes relevant. Scientists such as Paul Davies and Lawrence Krauss have explored the far future of the universe through theoretical frameworks that extend beyond direct observation. Their work emphasizes that while the universe's end may appear bleak at first glance, it also reveals the remarkable coherence of physical law. The consistency of cosmic evolution, from the birth of galaxies to the evaporation of black holes, reflects the stability and simplicity of the laws governing matter and energy. This stability offers a calming sense of order, suggesting that even the universe's slow fading follows a predictable and elegant path. Another domain worth exploring involves the possibility of long-lived, exotic objects. Some theoretical models predict the existence of particles or composite structures that could survive extreme environments for extraordinary durations. These objects may persist through the entire lifespan of the universe, drifting quietly through expanding space. Although their existence has not been confirmed, the idea of long-lived exotic particles adds depth to the universe's far future, offering a picture of persistence amid decay. When all these themes combine, they paint a picture of a universe that approaches its end gradually and gently. Each era moves smoothly into the next. Each mechanism slows as energy thins. Structures fade without abrupt transitions. Quantum fluctuations remain as soft vibrations. Dark energy stretches space with quiet persistence. Matter cools and drifts. The universe becomes a place defined by calm, silence, and deep time. Its ending resembles not an explosion or collapse, but a slow settling into equilibrium, a cosmic rest guided by the same laws that shaped its beginning.